Okay, guys, so this is going to be Chapter 1, Section 4. So you need to be on page 17 in your textbook, in your work or your ebook, in your workbook. I want you on page 11. Okay, so page 11 in your workbook. And again, I prefer that you do the skim and the vocab before I get started. And most of the stuff that you're going to need is in your textbook. Again, page 17 in your book or ebook. Now, this is the last section of this chapter. So once you finish in your workbook, you're going to do the chapter wrap-up, which is on page 14. So that just kind of pulls all the information together. Sometimes you're not going to be completely sure what to put there. Shoot me an email, shoot me a message. I'll put a discussion up, maybe on Padlet. I'm not quite sure how I'll do that, but we can talk about that part right there. Okay, so let's get started. We're going to talk about 1.4. Make sure you've got your notes ready. Click at a button. Maybe. There we go. All right, so chapter 1, section 4, scientific research. Some scientific investigations result in the development of technology that can improve our lives and the world around us. Notice it says some scientific investigations. So be sure, take a second, think about what do I know, what do I want to know, and what will I learn, which hopefully you'll come back. If you want, go ahead and put this on page 11. There's a big section down at the bottom in your workbook, and you can just put your little chart there. What do I know? What do I want to know? Come back and fill in what you've learned at the end. It's a really good way to study. We only have 2 essential questions for this lesson. How do pure research, applied research, and technology compare and contrast? What are some of the important rules for laboratory safety? We already covered some of that, but it's going to be good to go over it again. All right, your vocab. So synthetic, you should know. Take a second, think. Do you know what synthetic means? Pause. If you don't know what synthetic means, then that's totally okay. Synthetic means something that is human-made and does not necessarily occur in nature. You'll hear me call it man-made a lot. It is things that we have developed and invented. So anything synthetic does not occur naturally. And then the 2 new vocabs, which hopefully you've already gone ahead and written down on page 11 in your workbook, are pure research and applied research. Having that vocabulary, guys, is extremely important. I just want to toss this out there while we're in chapter 1. Vocabulary is not just for you to remember and memorize and then forget about. Vocabulary is important in the way that we communicate. Being able to use the proper terminology is really important. Plus, if you have a better vocabulary, guys, when you go to do interviews, you're probably going to get the job over somebody who refuses to use those higher order words. So keep that in mind. All right, so types of scientific investigations. Obviously, we talked about it. There's 2. The first one is pure research. Here's your definition, guys. Pure research is research to gain knowledge for the sake of knowledge itself. These are our academics, okay? That's what we call them normally at the college level. They are out there just to tinker around with things and see what they find out. I want to know more about the electron, so I'm going to go and do pure research over the electron and see what I can find. Let's tie this back to our ozone CFC situation. Scientists Molina and Rowland were motivated by curiosity when they conducted their research on CFCs and its interactions with ozone. So we didn't even quite know this connection if they hadn't been researching on their own. So no environmental evidence at the time indicated that there was a correlation to their model in the stratosphere. So nothing tied CFCs to ozone until they had done this pure research. They had asked the question, what's happening to our ozone? But by chance, these people were doing the research that tied this concept of the CFCs affecting ozone. That's how a lot of things happen. That's why communication is extremely important in science. If you don't publish your information when you're done studying it, how is everyone going to know? Just like we saw with the coronavirus, we didn't know how to treat it And we still are not completely sure of how to best treat it because we haven't gotten enough information published yet with the data from the testing, with the controls and independent and dependent variables. So you can see this is a real life situation now. Applied research is research undertaken to solve a problem. So this research is like, how do we get that vaccine? How do we get a vaccine that will keep people from getting sick from this virus? Or in the CFC situation, how do we have to affect the amount of CFCs to fix the ozone layer? So those scientists continue to monitor the amount of CFCs in the atmosphere and the annual changes in the amount of ozone in the stratosphere. Didn't mean to do that. So they continue to do their research to find replacement chemicals for CFCs that are now banned. I want you to take very good note here. CFCs are now banned because it was destroying our ozone layer. So chance discoveries occur when scientists obtain results that are far different from what they expected. You're trying to find one thing, but you happen to find something completely different. So this would be like Alexander Fleming discovering penicillin. Penicillin was not meant to happen, but he just happened to put the right things in with bacteria and it ended up killing it. So because he was able to kill the bacteria, he's like, I bet this could be used for bacterial infections. Or this could be used if somebody comes down with, a staph infection. Maybe it'll work. And now we know that it's a perfect medicine for bacterial infections. Another thing, what is it? Teflon. So, the nonstick surfaces that are on most pans, that was a complete accident. Never meant to make it, but that he was playing around in the lab and he made this substance that when it hardened, nothing stuck to it. So that's another chance discovery. And those are always the coolest. All right, so let's see. We've talked about applied. We've talked about pure research. I want you guys to look through the table on page 19 in your textbook. Okay, and you remember to get to your ebook, it's Clever, McGraw-Hill. Click on the book to open it and you open the ebook. So make sure you look at table 2. Those are, again, the same things that we went over with your safety test, and I'll be getting with those of you who still need to get your grade that you're supposed to have on your safety test within the week, okay? Now, the last thing that you're going to do for this lesson is you're going to go to, you're already in your book, you're going to click menu and homework, and the very last one there says video tracking a crime. I want you to go and watch that video, and then I'm going to ask you a question. You're going to come back to me, okay? So push pause now, go watch that, and come back when you're finished. All right, so as they've done this research, they've been safe, they've put in all their parameters to make sure they're studying and finding that one correlation they want. Applied research, so trying to solve this problem, showed that CFCs and some other chemicals are reacting with our ozone layer. In 1987, they signed the Montreal Protocol to phase out CFC use. So we can't put it in coolants anymore. We're going to keep it out of aerosols. We're not going to put it in certain sprays to propel them. So if you notice 1987, if you can read a graph, it falls between 86 and 88. If you look at this consumption, they started phasing it out, and the goal was to get it below, consumption below 200 parts per trillion, PPT. And then if you look, notice this graph has 2 axes to it. So if I'm looking at these values on the right, I'm talking about CFC consumption, the ozone depletion potential in thousands of metric tons. So sorry, that's 200 metric tons that we're using. We got below 200 in 2000. I'd like to see the updated graph on this. If any of you find it, send it to me. And let's see what it did to the CFCs found in Antarctica, because remember, everything moves from the equator. So it's going to compile over the poles. So CFCs in Antarctica went from 500 parts per trillion, and throughout that 15-ish years went to below 100 parts per trillion. So their efforts here didn't work? What do you think? What do you think about the efforts here to bring CFC consumption down? Did it work? Another part that we came up with after studying it for a long period of time, they found that the ozone thinning occurs every spring. Well, so it's getting thinner in the spring. What could be happening? What could be happening? Why? Why is it every spring? What do you think happens in the spring that it causes this ozone thinning to occur? What's going on in the world during spring? All right, answer that question for me. Push pause, answer now. Guys, every spring, temperatures start to rise. As temperatures rise, particles move faster. As the particles move faster, you get more and more CFCs moving around, so they're going to interact with that ozone layer even more. Okay, we'll talk about that when we get to gas laws more. I did not mean to do that. Undo. Let's go. The last little bit here, we've talked about how we conduct scientific research. We've talked about how we do experiments. How do we set up our experiments? So yes, chemistry has helped us determine what's happening with our ozone depletion. But it's also important for help finding cures for diseases or viruses or anything in the medical field that might come up that we might need to remedy. And another good big thing that we've done since about the 70s, we have reduced pollution to a great extent. We have taken it from being all cities were covered in a haze of fog and smog and just exhaust to being, you know, nice. Like I can look outside and I can see for a mile. Okay, that's what we're trying to do. We're trying to solve these types of problems. So what are the upcoming problems that we need to solve? Not necessarily me and you in class, but as the human race, what problems do you think that we need to solve? What problems are going on in the world that we need to solve? All right, so here are the questions I'm going to ask you here in a second. How do pure research, applied research, and technology compare and contrast? What's the same with all of those? What's different? And what are some of the important rules for lab safety? We've been over that, so just give me a few, okay? What do you find as the most important? Now, oops, I went the wrong way. That's it for this lesson. If you have any questions, again, I'm going to leave it out there so you can ask and we can come back to them in class. If you are confused on like how we're supposed to go through class, be sure you shoot me an email. And otherwise, I'll see you guys later.